So for the second week of CE 241, now we start discussing the atomic level structure of materials. And to be able to discuss the structure at the atomic level, at this scale, we first have to remember certain things that we had been introduced to in chemistry. So some questions that one might ask is what promotes bonding of atoms? So why do atoms bond to each other? What types of bonds are there? And what properties can be inferred from bonding? Which properties, say, of a real material can be determined from the properties of the bonds or the types of the bonds that its atoms make? So it is useful to remember some things about chemistry 107 or earlier chemistry courses. So it may be a good idea to review your notes at times. Now, when you find any material in nature or in the artificial world, one method of classification classifies materials into categories that are referred to as metals, ceramics, polymers, and semiconductors. Now, here, ignoring semiconductors, which is a special group of materials, a category that is not very commonly observed, and ignoring certain other maybe material classes that are not on this list, most every material that you will find that is handed to you by a friend will be either a metal, a ceramic, or a polymer. So when you quickly look at examples, a steel structure is made of steel structural members, such as steel columns, and the steel columns will be made of a combination of different metals, such as iron and some other metals, and those metals will inside them have metallic bonds. So all metals are made up of metallic bonds, or metallically bonded materials are metals. Now, ceramics, you may think of as your bathroom ceramics, like your bathroom tiles, or porcelain plates, or bricks in construction, or concrete, can be classified generally into the category of ceramics. So you notice how a porcelain plate and a brick in construction, a red construction brick, are different in their general properties than a metal like an iron or a steel bar. Now, a polymer, an example of a polymer can be the PVC window frames that you have in your houses, or it could be a plastic bag, or various other such examples. Anything that you refer to in everyday life as a plastic is under the category of polymers. In construction, a common example of this is asphalt. So the black goopy material, or the black material that holds together rocks in the roads, is a polymer. Now, if you look at the different materials under the category of polymers, you will see that they have also similarities with each other, but not so many similarities with those materials that are under the category of ceramics. You might think that concrete and brick are hard, but they tend to break when you hit them onto a harder surface. Hence, ceramics are able to break, but they are rather hard or rather strong. Metals are strong or hard, but they don't tend to break, but rather they tend to bend or they tend to change their shapes when they are forced. Polymers are generally weak. So when you think of a plastic bag, you can tear it with your hands. If you have a plastic PVC pipe and you try to break it, you might not be able to break it into two pieces, but you'll easily be able to change its shape without applying too much force, just with your hands. So suddenly you see that there are tremendous differences between these different categories. And the number one explanation lies in this pyramid on this slide. So materials that are metals have the metallic bond. Ceramics have ionic and covalent bonds. So they tend to fall in between the two extremes, but they don't have any metallic bonds, hence they won't have the properties that metallic bonds provide. Polymers have covalent or secondary bonds. Secondary bonds are weaker. The other three, the metallic, ionic, and covalent, being referred to as primary, or being stronger than the secondary. Hence, you might imagine that ceramics are not like metals, and they are not weak because they are a combination of a strong and another strong type of bond. But polymers are a combination of a strong and a weak bond, or a secondary bond. Hence, they are not very strong in certain ways, plastic. And metals are made up of metallic bonds, which gives them completely different properties. So different types of bonds that you've seen up to now give different categories of materials their distinct properties. So inside a material, you basically have, forming up the structure, you have atoms, which are atoms of different elements. And then you have molecules and compounds made up of these different atoms, either one type of atoms or more than one type of atoms. So the distinction between a molecule and a compound is that a molecule is formed by bonding between two or more atoms, and it is referred to as the smallest unit of a chemical that retains the overall chemical properties, which will have the same chemical behavior related with this property. And a compound is very similar in that it is made up of different elements, or it contains two different types of elements or more. And the idea is that a compound can be chemically decomposed into simpler substances. So continuing to remind ourselves, or to sort of remember our previous chemistry classes, an atom has very small mass. It's made up of electrons and protons and neutrons, and there's something called the atomic number, which says the number of protons or the number of electrons, to balance each other out as plus and minus. And the atomic mass unit is one way of counting the mass, or referring to the mass of atoms of different elements. And it is fixed as 1/12 of the mass of the carbon atom, which is known or said to have about 12 gram per mole mass. Hence, one atomic mass unit in one atom is equivalent to, or is equal to, 1 gram per mole. Hence, the atomic weight is the mass of a certain number of atoms or molecules. And this is the famous Avogadro's number, and is 6.023 times 10 to the 23 molecules. So then when you have this many atoms of carbon, you end up with 12 grams, hence the definition of 12 grams per 1 mole. And this is 1 gram per mole for something like hydrogen. Now, these portions we just skip through quickly. These are of significance to understand why things bond, or why things don't bond together, why different atoms don't bond together. So they're tremendously important in determining what bonds are possible, but they're not necessarily very, very related to what we discuss later in this set of slides. But so electrons are at a certain distance from the center of their atom and the atom that they belong to. So the center is where you have the charge and the mass, the nucleus, and you have the balancing negative charge and the very small mass or very small amount of actual substance revolving around this mass that forms up your atomic volume. And probabilistically, you have distances which represent certain energy levels, certain distances from the center of the atom at which a certain number of electrons all reside or can be found, again, probabilistically. Now, these, as you remember from chemistry, have different names like K, L, M, N, etc., with an increasing distance where the bottom of the slide is the center of the atom. And the more the atoms you have, the greater the size or the radius of your atomic sphere gets, because each new electron, or not each new one, but once an electron, once a shell is full, new electrons have to be placed or can find a position for themselves in a different energy position at a greater distance from the center. And naturally, the lowest available energy state is occupied by an electron, the lowest possible state. So it starts filling from the bottom up. And you remember names like 1s2, 2s2, 2p6, etc. This is the number of seats that can hold the electrons, and you have one seat for 2 electrons here, etc., etc. So then, the electron configuration, meaning the arrangement of electrons, is what you would refer to as not stable for most elements, basically for all other than the ones you refer to as the stable or noble or inert elements, such as helium, neon, or argon, etc., which have full shells and don't have any partially full shells. Anything that's not noble has a certain arrangement where a shell is partly full, meaning it is able to take on new electrons, or it is able to lose the electrons from that shell to drop to the previous noble condition. So then this tells us that there is a significance of the outer shell, which is referred to as the valence shell, which is usually not completely filled. And if you have a few spaces remaining there, then again you can get extra electrons or you can lose the electrons that you already have at that distance and essentially become a smaller ion, or let's say for simplicity, atom. So you could get full and stable, or you can lose a few electrons, get smaller, and become stable. Both are possible, but depending on how much effort this requires, the transfer of how many electrons to or from the atom will determine which one is more likely to happen. So the electrons in the outermost shell are the valence electrons, and they are filled when they are full, when they have no openings. We refer to this as a stable condition. And when there are openings, or when there is a partially full condition, then this is referred to as an atom being open to reaction. So in the case of carbon, atomic number 6, you have 1s2, 2s2, 2p2. You know from previous classes that this is in such a position that it can lose these 4 electrons, or it could gain 4 more electrons. Hence, it's in such a position that it can move to become more stable. So, and the number of electrons, or this condition, is determined by your atomic number, where you fall. And if you have an atomic number of 26, then you start filling from the bottom up. And when you're done with the electrons you have, you look at how many openings there are, and you determine whether you are stable or open to reaction because of the number of valence electrons that you have. So these all fill, and you end up with a certain number of valence electrons that end up giving you your condition. So this is from previous knowledge. So then the periodic table, without having to do what we did in the previous slide, allows you to determine this, make this determination more quickly. So if you are in this column here, then you're able to give up 1 electron to become stable, happy, etc. If you're in this column, you're able to give up 2, and if you're here, you're able to accept 1 or accept 2, etc. So then lithium is not as happy as it could be if it loses, if it gives up 1 electron by forming a bond with someone that will be willing to take that electron, such as those that are able to accept 1 electron, such as fluorine. And fluorine will be happier by taking 1 more electron to become more like its closest noble neighbor, neon. Hence, they will both be happy to form lithium fluoride. Or lithium, in the presence of chlorine, will be happy to form lithium chloride, and so will chlorine, because it is lacking 1 atom. So again, this tells you why you get sodium chloride, but why you don't get sodium phosphate at a 1-to-1 ratio. So you could get sodium and phosphorus to bind, but you cannot get NAP, because NAP does not put sodium or phosphorus in a situation where they are both happier. But you can get sodium fluoride, sodium chloride, sodium bromide, etc. So then if you have calcium and you have chlorine atoms, because this likes to give up 2 electrons and this likes to accept 1, the happy common stable form becomes CaCl2, because Ca gives 2 electrons, hence you need 2 chlorine atoms to take on the electrons, one each, to become ionic form and form calcium chloride, CaCl2. Again, CaCl3 is not likely, and is not possible, and CaCl at a 1-to-1 ratio is again not very meaningful because of this simple observation of places on the periodic table. Okay, so then you have the idea of electronegativity, and this is a discussion of how much or how little you want to acquire electrons. So if you wanted to say what is the difference between lithium and sodium when they are both in the presence of fluorine, there is a difference in how much they want to take electrons, and this difference is explained by electronegativity. So you notice that the difference in the horizontal direction is greater than in the vertical direction when you move 1 unit, which makes quite a lot of sense. So then, another important observation is that the valence electrons determine not only your willingness to bond and become stable, but they determine all of your properties once you bond, such as your chemical, electrical, thermal, optical, etc. properties. So, when you have 2 or more atoms or molecules that link together, they form a material, and depending on how strongly they form this bond and how much they pull each other and how much they want to retain their bond length or the distance between 2 neighboring atoms, the resulting material is a gas, a liquid, or a solid. So you might imagine that a solid is not possible to deform easily. Hence, a solid has a greater desire to maintain the distance between the neighboring atoms. So in iron, which is formed of iron Fe, the atom iron atom, connected to another iron atom, connected to another iron atom, connected to another iron atom, the distance between one iron and the other iron atom is very specific and does not want to change. So if you do something like apply an outside force to try to change this, there is a great resistance to the change. Hence, the material is a solid. And in the case of O2, a gas, oxygen, the oxygen to oxygen length is not very critical or is not very resistant to change. Hence, if you try to compress or if you try to expand, if you try to introduce oxygen gas to a greater volume, or if you try to compress it into a smaller volume, you will observe that this can be done with small amounts of force. So the reason for this is because the desire to keep the same distance between the average 2 neighboring atoms is not very great in the case of a gas. And for a liquid, it is intermediate. It's more than for a gas and less than for a liquid. For a solid. So then, when atoms come together, depending on how they arrange themselves, you can have different shapes, different geometries. So suddenly notice that I was discussing topics that you've seen in chemistry, but suddenly this is something you're not so familiar with from chemistry, at least most of you. So when atoms bond and they form a chain-like structure, this is what you have in polymers. Now, we'll discuss in a few slides why or how you form a chain or you form other structures, and why some elements form polymers and the others form metals, essentially, will be introduced. But when you bond atoms in a three-dimensional pattern, in a pattern that's repeating in 3 dimensions, then this tends to form metals, or metals tend to form, you could conversely say, an atomic structure that is more like a three-dimensional array, three-dimensional geometry, rather than this long chain structure. So the, again, general idea is bonding between atoms is because of the desire, the tendency of all systems and the atoms that make up this system to take up their lowest energy state, to move to a stabler, lower energy, smaller volume position. So this is similar to you taking a ball into your hand and it dropping to a lower energy state, in our case, in this case, due to gravity. So then the rule that's followed is this rule of 8, which is the possession of 8 electrons in the outermost shell, ignoring the first shell, which has 2 electrons in its stable condition. All the other shells have 8 electrons in to be full. So then any atom will try to change its structure, its electron number, to get this, to satisfy this rule of 8. So if you have 5, 6, or 7 valence electrons, then you can accept 3, 2, or 1 electrons to become 8 total. And if you have 1, 2, or 3 too many, so if you're on the left-hand side of the periodic table, then you can get rid of these. And if you can get rid of these, then you can become stable in the underlying shell, in the shell below that particular shell. So the atom can become a smaller ion, can lose some volume, lose the outer shell, and still become happy, similar to the, again, closest noble element. So then, if you have 4 valence electrons, you can be of both natures. So you can go one way or the other. So materials that are there where they have 4 valence electrons, like carbon that we just saw, have special properties. They have special, there are certain advantages or certain peculiarities of such atoms. Silicon is a similar atom, like carbon has this nature. So atomic bonding, again, is primary or secondary. The examples of primary had been discussed. The example of secondary is, one common example is the van der Waals bond. So the van der Waals bond is something that exists in essentially every material. But in the case of metals, ceramics, and well, in the case of metals and ceramics, the primary bond existing is so dominant that the fact that you also get some secondary bonding is not of significance. So you do have it. In fact, you do have atomic bonding between the atoms of your fingertips, the skin atoms on your fingertips. When you rub your 2 fingers together, or when you put your thumb and your index finger together, there is some bond, but it is so weak that you're able to pull apart your fingers without feeling any pain or without damaging anything, because although bonds are made and broken, they are so weak that you can't really feel this resistance. However, if you glue your fingers together, you end up using a polymer in the glue, the polymer contains, in addition to van der Waals bonds in its structure, it contains some covalent bonds. And depending on the type of glue that you use, you may be unable to break those bonds, and you will get stuck with your two fingers touching each other. And if you try to break this, and the bonds inside the polymer, inside the glue, are stronger than the bonds between the glue and the skin atoms on your finger, then instead of the glue breaking, part of your skin will break and you will feel tremendous pain. So then this is all dependent on the strength of the bonds that you need to break. And if you have primary bonds at play, the secondary ones are not tremendously important. So an example of ionic bonding is typically given as sodium and chlorine coming together and forming sodium chloride. The two are attracted to each other by electrostatic force. You have a metal, sodium is a metal, and you have a non-metal. Chlorine is a non-metal. So then when you bring together a metal and a non-metal, they can form an ionic bond. So two metals or two nonmetals do not form an ionic bond. You can't get sodium and sodium, or sodium and potassium, or sodium and calcium to form a bond. Or you can't get those to form an ionic bond. And you can't get two chlorine atoms to form an ionic bond. Two chlorine atoms can come together to form chlorine gas, or a chlorine molecule with two atoms, but it will not be an ionic bond. Hence, it will not have properties that ionically bonded materials have. So also you can say that it forms between materials that have dissimilar electronegativities, meaning materials on the left-hand side and the right-hand side of the periodic table. Another good example is magnesium oxide. Magnesium is in the second column from the left, and oxygen is on the second column, the third column from the right. So it accepts two electrons, and magnesium gives two electrons, as shown here, to be stable. And they can form magnesium oxide, which is an ionically bonded compound. Magnesium oxide can be a rock or a powder, a solid it is. And if you look inside that solid, you will find magnesium and oxygen bonded together. And when you try to break that solid, it will not be easy because the ionic bond is a strong bond. So then this occurs between plus and minus ions, and electron transfer is necessary. A large difference in electronegativity was mentioned. And what you observe here is that the sodium losing an electron becomes actually physically smaller. Its volume, or its atomic or ionic radius, decreases. And the chlorine atom, by gaining an electron, becomes a chloride ion or a chloride anion, a negatively charged ion, and it becomes physically larger, and the two come together, pulling each other with what is referred to as Coulombic attraction. So this demonstrates the same process. On the left bottom side, you have larger chloride ions and smaller red colored sodium ions. And you see that they come together according to a certain pattern in 2 dimensions. It is shown like on the left. On the bottom right, you see this in 3 dimensions, which is what really happens, or which is more representative of what happens in real life. And you notice that there is a considerable size difference between the sodium and the potassium, sodium and the chlorine ion, so the sodium ion and the chloride ion. And you might imagine that this size difference, this volume difference, is also of some significance. So this will also become significant because it will explain later on in the course when you combine different sized ions, how they can come together or how they might not be able to come together to form an atomic structure. So then properties. Forces are electrostatic or coulombic. The ionic bonds are non-directional. So this was stated in the previous slide as well. Each plus ion is surrounded by as many ions, as many negative ions as possible. So what this means is, if you count how many red sodium ions surround this particular yellow chloride ion, you see 1, 2, 3, and 4. There's one in the back that you can't see and one in the front that's supposed to be here, but the structure being simplified doesn't show this. So due to symmetry, if you were to grow this structure in all three dimensions, you would see that each atom, each ion, yellow ion, would be surrounded by 6 red ions, and each red ion would be surrounded by 1, 2, 3, 4, 5, 6 yellow ions. So here the ratio of 1 ion being surrounded by 6 ions is not a golden rule. It is the case for sodium chloride, and the reason it is 1 to 6 is because because of the fact that you have an equal number of sodium and chloride ions in the overall structure, and also related with the relative size of the two ions. So if this were an ion that were significantly larger than it is here, so if the two radii of the ions were almost identical, you could end up getting a different arrangement. Hence, the rule is that in an ionically bonded material, as a function of relative ionic size and how many of each ion type exists on average, you have each plus ion surrounded by as many negative ions as possible, not always 6 as I mentioned. Hence, this is referred to as being non-directional. Now, non-directional could also be interpreted as such. There is no directional preference for this ion to position itself next to this other yellow ion. It does not say I have to be at a certain angle, like in the case of water, you might remember. Water has 2 oxygen atoms and 2 hydrogen atoms and 1 oxygen atom, and the hydrogen atoms are not at 2 opposite sides of the oxygen that is in the middle. So it's not a linear structure, but it is rather a broken structure with a weird angle of 104 degrees between the 2 hydrogens attached to the central oxygen. So that is not an ionic bond, and that requires that the angle always be 104 degrees between the positions of the hydrogen atoms with respect to the oxygen atom in the middle. Here, the only requirement, there is no angle-based requirement, there is only a requirement of maximizing the number of ions that surround an ion of opposite charge. So then, these bonds are referred to as strong, stable, etc. Well, strong and stable for the moment. Now, we haven't yet officially discussed what strong means, but you could say it is hard to break. Hence, anything that's ionically bonded in a large scale will also be strong or hard to break because it is made up of strong, hard to break bonds. So stable here means it is, again, mechanically or force related, difficult to break, or it could be also referred to as in some other ways, such as chemically, it may be less willing to react with other substances than a bond, than materials that are bonded with a less stable type of bond. Now, brittle in Turkish gevrek is the property of breaking without deforming very much. So if you try to break a porcelain or a ceramic plate, if you drop it on the floor, and if you drop it from high enough, it will break because you will have exceeded the strength of its bonds. But when it breaks, it will break suddenly, and it won't bend, and it won't be able to deform. But whereas a different type of material, such as a metal plate, will not break, but it might bend, it might deform a little bit. So brittle, here discussed much more later in the course, is the concept of a bond not being able to deform, not being able to lengthen itself, the distance between neighboring atoms not being able to increase, but the material breaking. So notice that you can be very strong, but you might not be able to change your atom to atom length very much. In that case, when you drop a ceramic plate on the ground, on the floor, it will either not break because it is strong enough, or if you drop it from a great distance, from very high up, and you exceed its strength, it will break because this type of bond is brittle. So you can be brittle, but you can be strong at the same time. Now, this bond, because it is a strong bond, because it involves this electron transfer, you have a high melting point. A high melting point is similar to being strong. If you have high strength, you will generally have a high melting point, and vice versa. You have poor electrical conductivity because the electrons that are shared, they're not shared. The electrons that are involved are transferred from one atom to the other. And when they are gained by the one atom gaining them, in this case, the chloride ions hold those electrons tightly and close to themselves, their centers. Hence, there is no ability to conduct electricity effectively. So they are poor electrical conductors, and this is the reason why a lot of electrical equipment is made of ceramics. So when you look at old electrical setups in old electrical equipment, you see a lot of ceramic members. And this is because they are poor electrical conductors, and they are strong and stable at the same time. So they can resist melting and resist breaking easily, but they don't conduct electricity effectively. So, and also what we mentioned about how it forms between different electronegativities. Hence, it cannot form between two members of the same type of atom. So then, this brings us to a graph that we discuss a little more later, where there is the graph shows the energy situation, the attraction or the repulsion energy, the desire for the atoms, the ions, to come together or to push away from each other. And you see that the net position of two ions with respect to each other is determined by a summation of the positive and the negative, or the pull and the push, or the attraction and the repulsion between the two ions. So on this graph, again, don't worry too much about this graph just yet, because we discussed this with an example at the end of these slides. But on this graph, we have something shown in green referred to as repulsive energy. The graph shows energy felt between the two ions. In, say, the previous example, between sodium and chloride, the two ions, the distance between them, between their centers, being referred to as interionic or interatomic separation, here given by the letter R, this position being the 0R value, hence this being where the two centers of the ions overlap, which is impossible. And if you look at a greater separation, so some position here, indicating some value between, some physical distance between the nuclei, or between the centers of the two ions. So the greater the value of R is, the farther apart the two ions are. At this point, at this separation, you look at the graph and you see that the value of repulsive energy is 0. The value of attractive energy, shown in blue, that is overlapped after this point, or that is that overlaps with the red net energy curve, is non-zero. Hence, at this distance R, when the two atoms approach each other, when the two ions approach each other, they feel each other. The feeling is a feeling of attraction. There is 0 feeling of repulsion. Hence, the material, the two ions naturally come closer. Then you look at this difference, at this distance between the two centers of the ions, and you see that now, having come closer, the net energy is an attractive energy. They feel each other, and they feel each other more strongly because they are closer together. And until this point, there is only attraction. But you notice that after this distance, there is, in addition to an attractive energy, there is a repulsive energy that grows, but in the opposite direction of the attractive energy. Hence, the net energy curve, the red curve, changes its shape, or changes its slope, to quickly have, at this point, or at this value of R, what is referred to as an energy trough or an energy minimum. And this is the point where the attractive and the repulsive forces, here realize this is an energy curve, the forces pulling and pushing together the ions balance each other out, and the net energy here at this point, so what is shown with E naught or E0, is referred to as the bond energy, roughly. And if you go to a smaller value of R, if you push the ions closer together, because the repulsion energy grows with a greater slope than the attraction energy, the net energy curve starts moving in the other direction, dominated by the repulsive energy. And you might imagine that this zone is unhappy because the atoms are too close to each other. Hence, they are net repulsing each other, pushing each other away. This zone is not stable or happy because the net energy is attractive. Hence, they're pulling together. And this point, and only this point, or this distance, is the distance of the two centers of the ions where both are happy. So this bond forms at this R value a stable happy bond, and this is referred to as the bond length. So this is the bond length of a stable happy sodium chloride ion, sodium chloride bond, and this is the net energy that they feel. Now you might imagine that the net energy is here, which corresponds to attraction, and this also makes sense because the net energy situation is that you have a condition where the net is the overall situation is that there is an attraction, there is a pull between the atoms, between the ions. Okay, so this, I won't get into the equation because we discussed that soon. So we said that this is the predominant type of bonding in ceramics. And as examples of ionic bonding, again, you have those that are here and those that are here that bond, such as sodium fluoride, lithium chloride, potassium bromide, etc., etc. Lithium, sodium chloride, magnesium oxide, calcium fluoride being similar, except because calcium has 2 extra electrons and fluorine has 1 too few, you need 2 fluoride ions to balance 1 calcium ion. So here you might imagine that when you try to draw calcium fluoride using spheres, like in the previous example with the yellow and red spheres for sodium chloride, the arrangement will be slightly different. The arrangement, so you can't immediately say how many ions or how many spheres will be surrounding a sphere of the opposite charge. Okay, so then covalent bonding is a little different. Covalent bonding happens between similar electronegativity, or certain types of atoms are able to bond covalently. An example is methane, CH4. And here the idea is, again, C needs 4 more electrons to become stable, and H needs to let go of 1. So H needs to take on 1 more to become stable. So in this case, they both need they both need extra electrons to feel happier, to feel stabler, etc. So this is shown by these energy shells. Hydrogen has only 1 shell, and carbon has 2 shells because it has more than 2 electrons in it. Because it has 4, it wants to take on 4 more to become stabler, whereas hydrogen wants to take on 1 more, and by sharing, by overlapping their energy shells or their energy layers or their critical distances from their centers, they're able to share the electrons to form what is referred to as this covalent bond. The electronegativities are similar or comparable, meaning they form between atoms that are not necessarily on the left and right hand side of the periodic table, but between different pairs of atoms. So a typical example of covalent bonding is when you have 2 of the same atom. So when you have 2 chlorine atoms, they form chlorine Cl2. Cl2 is the general representation of what you'd use for chlorine gas. And because each one is lacking by 1, they can share an electron and become a diatomic molecule. So then when you have 2 chlorine atoms, the only thing you can form is Cl2, but you can't form Cl3 or Cl4 or Cl all by itself. Cl all by itself will be incomplete, and Cl3 would not work because there's only 1 electron that can be that is needed, so you can't share electrons in a way to give you Cl3. So now suddenly you can have covalent bonds with when your valence electrons are 7, the number is 7, or when it's 6. But when it's 6, you get a slightly different situation. You have sulfur, it has a certain number of electrons, has a certain number of valence electrons, and it has a certain deficit. In this case, it has a deficit of 2 electrons. So the idea is that in this case, when you have 2 electrons missing, you can share 2 electrons, 1 with each neighbor, and this will allow you to form a chain-like structure. So in the previous example, note that you can form only 2 atoms together. You can't form a chain, but here, because you have 2 open hands, you can form a chain because each atom can share 1 atom with its neighbor on one side. So when we say a chain, it doesn't need to be linear. The idea is that it can form a one-dimensional structure. Note that here, what you form, the structure is 0-dimensional, like a dot, like a point. This is one-dimensional, and if you have n equals 5, such as arsenic, I guess, your atomic arrangement is such that you need 3 close neighbors to form sheets of atoms, because in addition to forming 1 bond with one side and 1 bond with another neighbor, in the 3rd direction, let's say perpendicular to the board, in the case where n equals 5, you can form sheets of atoms. You can form, you can essentially start forming a 2-dimensional layer. So if you had 1 atom at the center, it could make 1, 2, and 3 at 60 degrees to each other. It wouldn't have to necessarily be like that, but let's just assume that. And you could form a giant 2-dimensional structure. And when you have the very special carbon, or not shown here, but the very special silicon, then you have n equals 4, which says you can form a 3-dimensional structure. Remember, the tetrahedral arrangements from earlier chemistry courses, these work when you're able to form a greater number of bonds from each atom, or when there are atoms in the structure, like carbon, that are able to form 4 bonds. So the ethylene molecule, C2H6, is another example of an electron sharing situation. Hence, it is a covalent structure. Here, carbon shares not only with hydrogen, but it also shares with itself, where here you have a carbon-carbon bond, and you have multiple carbon-hydrogen bonds. So it doesn't mean that the 2 atoms have to be the same. Carbon and carbon can form covalent, and carbon and hydrogen can also form covalent. This is because of the special position of hydrogen and how it can complete itself to a stabler condition by gaining an electron. So then when we compare covalent and ionic, we see that this is based on electron sharing, not a transfer. It is directional in that each atom is surrounded not by the maximum number of neighbors, but a definite number of other atoms. In this case, carbon can have a certain number of atoms around it. It cannot have as many as possible, or it has to have a special number of neighbors, depending on how many atoms it has the ability to share, depending on its position on the periodic table. And those atoms, in reality, have to be at specific positions. So the atoms must arrange themselves in a particular geometry, in particular orientations. Hence, they can't just come together to form, to surround the atoms around them to maximize the number. They have to be arranged in a certain amount, in a certain fashion, and they have to be, each atom needs to be surrounded by a definite number of other atoms. Again, this bond is hard and this bond is strong, and it's not written here, but this bond is also brittle. So generally, this bond is brittle. It's not able to increase its length without breaking, etc. Now, the hard and strong is all relative. So here it's referred to as being slightly less than ionic. So technically, an ionically bonded material should be slightly stronger than a covalently bonded material. But it's not very easy to distinguish between the real life properties of materials simply by looking at the types of bonds they have. So it can just, for simplicity, be assumed that both ionic and covalent bonds are strong. And they have very high melting point. And they have, again, because all the electrons are shared, there are no free electrons wandering around. They have low electrical conductivity, and they form between certain types of atoms, like hydrogen and chlorine, or like hydrogen and oxygen. So the typical hydrogen and oxygen, H2O, has a certain angle between one OH bond and one OH bond, because this is directional, because there is an energy happy condition that needs to be satisfied. So the metallic bonding is yet another type. This occurs between metal or metallic elements, which are also here referred to as the electronegative atoms that want to give away their electrons. The electrons that are on the left-hand side of the periodic table, mostly. Or the electrons that have, more technically correct, this electronegativity required, satisfy this electronegativity requirement. So this is also sometimes considered to be a special type of electron sharing, so a special type of covalent bond. But here, it's not that one or two electrons, particular electrons, are being shared, but generally the whole valence electrons are shared. This is what's referred to in earlier classes as the electron pool. So the whole valence electrons are shared. There is a greater amount of electrons that are involved with neighboring, the electrons from neighboring atoms. But this is kind of similar to electron sharing in the covalent case, but like a special case of it. So then the electron cloud creates so the sharing of this electron cloud makes the situation such that you have each individual metal ion center does not really know who the electrons it's feeling or that's around it belong to. So there is a more common sharing going on. So this is a simplified showing of that. You have your metal ions like an iron ion or a calcium ion or a potassium ion or a lithium ion. And the plus charged ion is plus charged because metals become ions by losing electrons because they have too many electrons. The too many electrons are shared commonly. And the ions form a certain geometry, a certain three-dimensional pattern, an arrangement that's referred to as a crystal lattice. And they are held together by this electron cloud. So this here is two-dimensional. So they look like there is a certain rule of how they came together, but in 3 dimensions, it becomes more complicated or more, you start getting more options of how metals can have their ions come together. And a part of the class discusses later in a few weeks the different ways in which ions can organize themselves to form the atomic level structure in different metals of different elements. So then when you look at the properties of metallic bonds, it's based on electron sharing, but the sharing is among all atoms, not just the two atoms sharing one electron or two electrons. There is non-directionality, so it's similar in that sense to ionically bonded materials. Hence, there is a desire for the largest number of nearest neighbors. Hence, the idea why in different metals you have a different geometry in 3 dimensions of how the ions come together. In this case, because there is a sharing of a high number of valence electrons, not by particular atoms, there is a greater freedom of electrons to move, one can sort of simply say. Hence, there is high thermal and electrical conductivity, which depend on electron movement. Because ions do not share particular electrons, and electrons aren't shared by only 2 ions, but by more ions, they are located at a greater distance than each other. which makes them makes this the weakest primary bond, and which, because of this, makes the melting point lower than that of covalently or ionically bonded materials. Now, this doesn't mean that it is weak, and it doesn't mean that its melting point is low, but this does mean that a ceramic can have a melting point that is, say, 2,000 degrees, but the melting point of a metal is generally going to be lower than that. It's not going to be typically 150 degrees, but you can say that for many metals, it'll be hard to obtain a melting point that is higher than, say, 1,000 degrees or higher than 1,500 degrees, whereas the melting point of many ceramics is, their melting points are greater than 1,000 degrees rather easily. So then if you ask the question differently, if I were looking for the highest melting point material for a special application, what type of material would I look for? And the answer would be a ceramic, not a metal, and not a polymer. So then a ceramic would be partly covalent and partly ionic, but a metal would be metallically bonded, hence it would be weaker in that sense. But this doesn't mean it is weak. It just means in relation, it is somewhat weaker. Weaker mechanically, weaker force-wise, easier to, let's say, break the bond, but not very easy. So then, I won't go into the detail of this, but if you want to get even further confused, real materials in real life, depending on what atoms they're made of, for example, magnesium oxide that we had said was an example of an ionic material, because of the positions of magnesium and oxygen on the periodic table, and using an equation that's not included in this course that takes into account their electronegativities, can be said to be 70% ionic and 30% covalent. So the idea is, if you combine magnesium and oxygen, the difference in their electronegativities, listed in the previous periodic table slide a few slides back, determines how ionic they are. And if you choose very different atoms which have very different electronegativities to form such a bond, then they will end up with a greater ionic nature and a less of a covalent nature. What this means, or what I want to say by this, is that until now we've simplified everything, but actually it's not completely true that a material, so when two atoms come together and they have some interaction, this could be partly a transfer or it could be partly sharing. It doesn't have to be one or the other. Nature is a little more complex than that. But this still does not change the situation that the type of bond that you have determines the type of behavior that you can expect from this material. So when I know that magnesium oxide is formed by magnesium and oxygen, and they're on different sides of the periodic table, I immediately know that this is an ionically bonded material, mostly. And immediately I say, well, if it's ionic, then it is high melting point, high strength, low electrical and thermal conductivity. So then it's better than nothing that you can say just by looking at the name and their positions of the atoms in the periodic table. So secondary bonding, I won't go into the detail of this, but this is where you have certain attraction situations that happen for short periods of time between materials. So these bonds form and break and form and break. And the one case that I want to mention for secondary bonding is that in the case of polymers or plastics, which we had said was a combination of secondary and covalent bonds, you have a structure which is like a chain structure, mostly made of carbon and some other atoms attached to carbon, but like a chain of carbon and another chain of carbon, which are held together by the weak bonds, the van der Waals bonds. So the idea is, if you say, is a polymer strong? The answer is yes and no. So a polymer, like a plastic bag or a PVC pipe, is weak enough that you can separate one chain from the other because they are not bonded strongly. But it is also strong enough that if you try to break this chain, it will resist tremendously. So then another important factor in polymers becomes how these chains are arranged and how they come together. So in the follow-up to this course, where you start discussing real materials, when we come to the topic of polymers, we will mention that depending on how these chains are arranged, you can have polymers behave to be more strong and more dominated by their covalent nature, or you can have them to be weaker, to be more dominated by their secondary bonded nature. But the idea is that this is universal to all atoms and molecules, and they're so weak that they can be neglected where other types of bonds generally exist. Okay, so you can go ahead and read through these notes. This is a refresher of chemistry, and you can also do the same for hydrogen bonding, which is again a sort of special scenario. So then we summarize. We say that as you change the type of bond, ionic, covalent, metallic, secondary, the bond energy, which is related to how much energy is felt between, how much attraction energy is felt between two neighboring atoms or ions, hence which is related to how strong you are or how high your melting point is large for ionic, and a little lower for covalent and metallic, deemed variable because it is large for diamond and small for other examples. Also for different types of metals, tungsten, quite high energy, quite strong, pull between the atoms, between the two metallic ions. Mercury, liquid at room temperature, indicating that the pull between the atoms must be small, but very small for its secondary. And then you look at certain properties, you see non-directional, but for these you have a different coming together rule, a directionality as discussed in the previous slides. And as examples of the different examples of substances that are held together by the different types of bonds, you have sodium chloride and magnesium oxide as ionic, and you see melting points that within themselves vary, but in some cases you can see a melting point of up to 2,800 degrees centigrade. This is significantly high. And when you look at the energy, ignore electron volts per atom, etc., but focus more on this. Using joules as an energy unit, per mole of the substance, so per a certain number of grams of this substance and certain number of atoms of this substance, the energy that you have in kilojoules, a certain energy unit, is higher than in the case of covalent and metallic, but much, much higher than in the case of van der Waals and hydrogen bonded. So you see that mercury, which is a liquid indicating it must have a weak bond, has indeed a low bond energy, whereas iron has a significantly higher one, and tungsten has very high within its own category, but still lower than materials that are examples of ionically bonded, that have ionic bonds that keep them together. So you might be surprised that table salt, sodium chloride, has in fact very high bond energy and high strength. So when you think of something being strong, it might not immediately be obvious. You might not be thinking of strength in different conditions the way, so you might be misjudging certain substances, thinking they're weak, where they're actually quite strong. You see that the bond energy in carbon, shown simply by C, or in diamond, shown simply by C, is lower than that in magnesium oxide. So this, you see also that there are overlaps. Certain members of certain categories are higher than certain members of certain examples in a different category, indicating that things are not very simple. You can't just simply say everything that is mainly ionically bonded would always be stronger than something that is metallically bonded. It's not as simple as that. There are other factors at play, some of which we discuss in upcoming weeks. So again, to summarize, metals, ceramics, and polymers make up about 90%, 99% of the materials that you can encounter in your life. And these three categories are defined by these four bond types. And by knowing the bond types and the categories, if you can classify something that you observe, something that you see, a material that you have at hand, into one of these categories, then you can immediately assume things about it. For example, when I say that asphalt, the main black substance in the asphalt roads that we have, is a polymer, if you believe me, you will already immediately know that it will behave similar to other polymers. And because of their secondary bonds, all polymers have low melting points. This doesn't mean that they completely disintegrate, because the covalent bonds are strong, but the secondary bonds that hold together the chains of carbon that I showed a few slides ago will give and will separate the chains from each other, and you will have melting of polymers or burning of polymers if you try to subject them to high temperature. The polymer foam, in the introduction videos, the lightweight insulation foam started catching fire when we applied a flame with a torch to it. And the reason for that was because it was a polymer. If we had applied a flame using a torch to a ceramic, like a brick, it would not catch fire and it would not melt until a very, very high temperature was obtained. So for a metal, it would not have caught on fire, but it would have melted, or it would have softened at a high temperature, but not as high as a ceramic. So the category is related with the bonds and vice versa. And knowing this, understanding this slide here is crucial to understanding what to expect from a new or or an unknown material. Another example of a property of real materials that is related with bonding at the atomic level is thermal expansion, or the coefficient of thermal expansion. So the coefficient of thermal expansion describes the ease or difficulty with which a material changes its length due to the increase, an applied increase in temperature. So an increase in temperature is possible via providing heat energy to the sample. So the bar here, held glued onto a fixed surface, to a wall on the left-hand side, is heated from its unheated state, its resting state of temperature 1 to a higher temperature of temperature 2. And as a result, it increases its length. So in reality, what happens is that this increase is not just a single linear increase, but rather it is a three-dimensional increase. But in this case, for simplicity, we just focus on a linear case. So the change in length, delta L, divided by the original length, L naught, is equal to a coefficient related with the ease or difficulty with which thermal length change happens, times the difference in temperature applied, so delta T, or T2 minus T1. So if this value is small for a given temperature change, say 10 degrees, the length change, say in percentage, is going to be small. And if this value is large, then it is going to be large. So having a large coefficient of thermal expansion indicates that material is less resistant to expansion. Similarly, you could say the same thing for contraction or shortening. If you have a large value of alpha, when you have a negative temperature change, you will get contraction, shortening, and it will be less resistant still, so you will get a greater length change, but in the opposite direction, a shortening direction. So then when you compare a hypothetical blue and a hypothetical black material represented by these curves here, the minimum energy, or the bond energy, of the blue material, or the blue atom pair, is lower in absolute values because it is smaller. This makes it easier for the bond to grow in the positive R direction. Hence, this slope here is smaller than the slope here, which means to move from, say, this atom separation to this atom separation, in the case of blue, about this much energy needs to be provided, whereas in the case of black, this much energy needs to be provided. So a greater amount of energy, meaning a greater temperature change, is needed to be applied to get the same length change, indicating that the black one has a smaller value of alpha. So the alpha is related somewhat to the slope, not at R naught, but to the right of R naught, or more correctly, you can see in the in relevant textbooks that alpha is related with the asymmetry of this energy trough. So the more symmetrical it is, the less length change one will observe. Hence, again, here, because the symmetry of the blue here around the part of the curve that corresponds to R naught is less than the symmetry here, it has a larger alpha, again meaning less resistance to expansion. So to summarize the primary bonds, we see again that we have ceramics, metals, and polymers. And ceramics have large melting points, large E values, here E being the bond energy, and small alpha values, thermal expansion coefficients. Metals, because we said have slightly lower strength in their bonds, they tend to have lower E values. So we refer to them here as not large but moderate. And correspondingly, they have moderate values of Tm and alpha. Whereas polymers, because of the secondary bonding involved in them, they tend to have small Tm, small bond energy, and large alpha value. So as an example of how the properties of real materials are affected by the bonds they have, we can use the property of melting point. So melting point is the temperature at which a given material melts or transitions from a liquid to from a solid to a liquid. So the idea is that melting point is where the atoms that are quite close to each other in a solid become distant to each other. They get farther apart, not so much that they become a gas, but far enough from each other so that the bond length represented by R from the center of one atom to the other atom grows to a significant value. So this process requires energy. Energy here is given in the form of heat energy that increases the temperature that eventually leads to melting. On the previously shown energy versus interatomic spacing or distance graph, so represented here by R, we have two materials represented by the blue and the black curve. And the blue curve, as you see, requires this much energy from its energy minimum to an energy value of 0, which represents no feeling, no attraction or repulsion essentially between the two materials. So you imagine that melting is related with movement in the positive R direction from the R naught stable position. And in both cases, this is true for both the black and the blue curve. But for the black curve, to achieve, to approach a value close to energy equals 0, which could represent the melting process or the melted liquid state, the amount of energy that needs to be provided, hence the vertical distance, is greater than in the case of the blue material. Hence, the blue material is said to have a smaller melting point because it has a different type of energy versus R relationship, which is related with the type of bond it has. So you could imagine that this is a weaker bond without knowing anything else about the material or the example at hand. And the black curve represents a stronger bond. The reason I say weaker and stronger is because if you were to try to physically separate by application of force, if you were trying to separate the two atoms in the black material, you would again need to provide this much energy, whereas in the blue material, we would need to supply only this much energy. So this energy needed to break the bond can be the energy given by heat to break the bond to get melting, or it could be the energy needed to be given by application of physical force by pulling or pushing on the material. It doesn't really matter. Energy is energy.